Hello everyone, welcome to Semiconductor Device Simulation. This is Lecture 3, Poisson's Equation and Newton's Method. In this lecture, first I will review the nonlinear Poisson's equation, and then I will introduce you Newton's method and how to use Newton's method to solve Poisson equation. In the end, I will show you some code demonstration. In the previous lecture, we have learned how to solve linear Poisson's equation, where we have neglecting N and P and assume complete ionization. And in this lecture, we will add back N and P so that we get our complete form of the Poisson's equation in semiconductor. This equation is a nonlinear equation, since N and P are both nonlinear functions of EC and EV. It can either be expressed using Fermi-Dirac integral or using exponential by Boltzmann approximation. To be noticed that in this lecture, we still assume complete ionization to simplify our calculation. Then how should we solve this nonlinear Poisson's equation? Since it is nonlinear, we cannot directly solve it as ax equals to b, and we just do an inverse matrix to append x. So we need to solve it iteratively using the so-called Newton's method. So what is Newton's method? It is a numerical method to solve nonlinear equation. F, which is a function of g of x, equals to 0. And to solve it, first we will start with an initial guess, x0. So now if we plug in x0 into this nonlinear function g, we will get f0 equals to g of x0. And if our initial guess is not good enough, so that the f0 doesn't equals to 0, now we will keep finding the next x by using the derivative information at x0. So here we were using a finite difference approximation of the derivative at x0, so that f0 prime, which is this g prime of x0, can approximately be equals to 0 minus f0 over x1 minus x0. So by using this approximation, we will be able to calculate the x1. And we can continue this process to xn plus 1, so that xn plus 1 will equals to xn minus fn over fn prime. And we do that till now our fn is very close to 0, or the xn plus 1 minus xn is very close to 0. So typically we will set some tolerance or criteria to determine that whether our answer is close to 0 and we can stop our simulation. And here is a simple example where I'm using this Newton's method to solve a quadratic equation. For quadratic equation, we know that there are analytical solutions we can get. So I will use those analytical solutions to verify my Newton's method simulation. And here you can see that based on different initial guess, whether we start from x0 is 0 or minus 1, we will be able to end up with a different final solution. This is because that in this system, we have two solutions. So depending on the initial guess, our solution will go to different direction and end up into either one of these positive or negative solution. And you can also see that the analytical solution is very close to our calculated solution. Okay, so now we can apply this Newton's method to solve the Poisson's equation. As I mentioned earlier, we still assume complete ionization to simplify our calculation. So in this Poisson equation, we want to solve for EC. Therefore, based on the equation we have derived in previous slides, what we will get is delta EC, which is EC at n+1 iteration minus ECn, will equals to minus Fn over Fn prime. And Fn is the equation we want to solve, and the Fn prime is the derivative of that equation. So after substitute Fn and Fn prime into this first equation, we can obtain this linearized Poisson equation for us to solve it directly. So in this equation, you can notice that now the only unknown here is this delta EC, which is the ECn+1 minus ECn. All other variables, such as n prime, p prime, ECn, n, and p, can be calculated from the previous EC, which is the ECn, that is a known variable. And now we have linearized this Poisson equation so that it can be directly solved as a linear AX equals to B equation using a linear solver. So how to calculate N and P? When using Boltzmann approximation, N and P can be expressed using a simple exponential function. And when calculate it using complete Fermi-Dirac integral, now we can notice that there is a relation for Fermi-Dirac integral that the derivative of Fermi-Dirac integral with an order of I is actually equals to the Fermi-Dirac integral of an order of 1 minus 1. So in this case, N and P can be expressed using Fermi-Dirac integral of an order of 1 over 2, and their derivative will be expressed using Fermi-Dirac integral of an order of minus 1 over 2. Okay, so the last few slides, I'm going to show you how to use code to implement this Newton's method. And so most of the part of this code will be similar to the previous code I have shown you for linear Poisson equations, so I will not repeat them. I'm just going to show you the part that you implement this Newton's method. So to solve it using Newton's method, we need to construct those matrices using our EC/EV from our previous iteration. So we can calculate N and P and Dn and dP. Here I'm using Boltzmann approximation. And then using those calculate NP, Dn, dP, I can construct the left-hand side and the right-hand side of that linearized Poisson equation. And then you can also apply a Dirichlet boundary condition. In this case, it will be a barrier height at a contact. Then using a linear solver, we can obtain the delta EC for this iteration. And the error for this calculation will be calculated from our delta EC. And then we update the EC to the new value and then return it so that you can use it for the next iteration. And here is some simulation result. And so in this simulation, I set the tolerance to be 1e minus 6. So the simulation, the iteration will continue until our error is smaller than our tolerance. And here I'm giving you an example of a simple PN junction with a contact Schottky barrier. So you can see that using Newton's method, we'll be able to calculate the band structure of a PN junction. Then I'm showing you another example here. Now I'm not using Dirichlet boundary condition to set the contact barrier. Instead, I use a Newman boundary condition. So that in this case, you can see at least two boundary. Now, due to a Newman boundary condition, the EC and EV at these 2 points are flat. That is because Newman boundary condition will set the derivative at these 2 points become 0. So you can see some ideal PN junction band diagram that is very close to what textbook will show you.